Hello, everyone. My name is Jaehyn Sim, and I want to talk about Postgres-powered AI, running end-to-end AI platform with help of Postgres on Azure platform. I'm currently leading engineering team here at Ikigai, and I want to share our story because it will give you a lot of insights if you're trying to build and develop an end-to-end AI platform using complex data types and complex AI workload. So why don't we dive right into it? As I said, I'm leading engineering team at Ikigai. Been here with our company for about 5 years, developing our AI platform from top to bottom, and currently I'm living in Boston. I wanted to quickly talk about our mission to give a more context to our audience. We want to bring AI to anyone, meaning there are a lot of AI tools that's being developed out there, but we feel like there are not many solutions that is targeting for the old enterprise data problems, which is for tabular data and structured data. So we want to design a solution that is specific for multivariate tabular data and then time series data. And we want to talk about how we made it happen. Where we started is we wanted to make an AI platform, an end-to-end AI platform that is specifically built on AWS as a SaaS offering, like 24/7 running types of SaaS offering. We wanted to enable business users and data scientists work seamlessly on one platform, meaning they can hop onto our hosted platform and then they can edit data, ingest data, and process the data pipeline, analyze by visualizing and interacting with what they came up with, and all this good stuff. While we're doing this, we faced a few challenges because we wanted to label ourselves as an enterprise AI platform. To explain the types of challenges we face and how we mitigated them, first I wanted to explain how we implemented our AI platform using Postgres, and then introduce the types of challenges we actually faced, and then talk about the timeline, how we mitigated them, and how we actually adapted to the Azure's environment. This is how our AI platform architecture looks like, and I want to start by explaining why we chose Postgres when we actually start implementing this platform 5 years ago. So the first thing is we all know Postgres is fast and scalable, but then why we wanted to put extra focus on was predictable portion. We're SaaS offering, so we are running our platform as a hosted service 24/7. That means it has to be reliable, and Postgres' reliability on the performances, it came in really handy. And the second big thing was we wanted to maintain SQL database. It's easier to use and familiarity, but also we want to leverage the power of JSON support that Postgres has, because we needed to work with unstructured data a lot using raw data from the user side. And we're going to dive into this a little more later. And another thing is a great community support. And when I say great community support, it's mostly language support, the programming language support, and the open source support. And we're also going to dive into this later as well. When we define how we want to support AI ML workload in our platform, we always talk about 4 different pillars: data ingestion, data processing, and the actual AI ML workload, including model training and inference, and also data interfacing at the end of the pipeline so that you can analyze with the results. And we're going to dive into each section and how we're going to talk about how Postgres enabled such workload and the steps in the pipeline. In our data ingestion, there are 2 different types of way of interacting with data. The first thing is the data connector. You can connect to different data sources that lives outside of the platform in secure and scalable way. And Postgres play a lot of part here because different types of data sources, for example, Google Sheet or Google Ad connector, they have fundamentally different types of requirements and metadata. And we wanted to still utilize SQL so that we can handle multiple rows, scalable and easy to use interfaces in programming language. But also at the same time, their definition looked too different. Do we want to leverage different types of database on top of our metadata just to handle these things? We didn't want to. So Postgres is a good choice that we can utilize because Postgres JSON support is not only fast, so we didn't really lose any performances, but that we can be really creative because you can actually also query on top of the keys that is inside of the JSON field. So it enabled a whole lot of the basic needs that we had for unstructured data without changing any infrastructure. And also on top of that, the open source tool that we're using, Airbyte, also utilized Postgres as internal states and metadata management. So it was a big plus for us because we didn't want to manage like different types of database inside of our platform. We wanted to kind of unify one primary database choice. Also, our dataset management, we enable users to host their dataset inside of the platform. When they do that, they store different types of metadata storages, including file types and data types and data format. And these things come in really handy because when user wants to download their data, we have to do a different types of processing to support them. And yes, so dataset. So we also leverage the JSON support for this, and also inside of our Postgres database. And data processing. To be fair, data processing, there are not a lot of benefit that we got from the Postgres itself, but one thing. In our platform, there are two different ways of executing user pipeline, which is remote cluster, a high volume pipeline run using remote cluster called Ray, and a low volume interactive workload using the local Python executor. The problem is the same pipeline can be ran in two different scenarios at the same time concurrently, and those two pipeline runs has to access the metadata that is stored in the Postgres all the time. There can be race condition. There can be race condition, but then because of ACID compliancy that Postgres enables, we didn't really have to worry about it, and also we didn't have to come up with a whole lot of locking mechanism just to support this concurrent way of running two pipelines. Moving over to AI ML workload. So this is, I guess, the best part that the biggest part that we got benefited from using Postgres as our metadata data table. In summary, a need to handle unstructured data. We wanted to handle unstructured data, but still want to use traditional RDBMS experience. This was this is the place where like we actually felt this to the heart. So we have our models trained and making predictions in our platform. And for all those models, different types of model have different sets of hyperparameters. And different hyperparameters like looks very different. Like if you compare traditional linear regression models and ARIMA-based like time series model, they're going to have just like night and days. They don't share any variable together, and their structure looks too different. So we're facing the same problems again. And all models, different definition requirements, they're stored in DB. We maintain the performance by utilizing Postgres's JSON support. And on top of this, each models, they can have different versions, and different versions can be utilized at the same time. So the problems that we had for concurrency problems, race condition types of thing on the data processing, that benefit that we got from Postgres also applies here as well. So multiple rows use it at the same time, and also each row having their own hyperparameter definition truly enables us to work with different types of model concurrently in one platform in a scalable manner. And finally, data visualization with Postgres. In our platform, we leverage multiple different types of open source tools so that we can provide the familiar interfaces to our users with the result they have from their pipeline runs. So first thing is data interaction. We're utilizing this open source tool called Jupyter Hub. And what it does is that it spawns the IPython notebook so that user can interact with the snapshot of the data in between of their workload, in between of the steps inside of the pipeline by just using the Python code base. And also we enable data visualization using multiple different types of dashboard vendors, including Superset or Plotly Dash. The good thing is that all this open source tool, including JupyterHub and Superset, utilizes Postgres has an option of internal state and metadata management as a Postgres database. And also for IPython notebook, for data interaction part, their definition is in JSON format, the IPython notebook's definition. So we can store that inside of a Postgres table with the notebook metadata. And for data visualization side, they have a different types of metadata that is stored with our dashboards metadata, and different definition between Superset dashboards and Dash dashboard. These get stored inside of our Postgres table as well, leveraging the unstructured data support of Postgres. So now we covered how Ikigai built end-to-end AI/ML workload handling utilizing Postgres, but then are we ready to solve the enterprise level problems? So the answer was no. And I wanted to explain what kind of challenge we faced. So coming back to the previous slide where we wanted to bring AI to anyone, including enterprise users, the problem that we face is that we wanted to operate on enterprise data, as in your own data, instead of enterprise setup. And the problem is not all the enterprise wanted us to provide a SaaS offering. They didn't want to get their data, they didn't want their data to leave their environment or their platform, and they want their data to stay there so that we can install our platform in their environment. So there's two methodologies here. So how we started is that we make our hosted service as a SaaS offering, meaning we have our platform implemented on top of AWS, and your user has to come on our hosted website and utilize our service. But then we wanted to switch over to BYOC, which means that bring your own cloud. What we would have to do is we're going to have to make our platform that is portable enough so that it can be installed in any different types of environment, which is an enterprise user's environment. And by doing this, their data doesn't have to leave their environment, and they can still leverage the power of Ikigai's AI platform. So our decision is that we wanted to make our platform better and by making it portable, but what's going to be our solid target? So we want to make our Ikigai platform compatible with Azure first, because as you can see, Azure, not only Azure is really popular in industry, but also we actually have two concrete customers that's asking us that they wanted us to install our platform on their Azure environment. So we decided to explore the possibility how we can transition our heavily AWS-based Ikigai platform on top of Azure. And while doing that, what we wanted to evaluate is that the flexibility of the platform. So far, our AI platform was very, very focused on the two aspects, which is scalability and interactivity, as in user can still interact with their data and their models while maintaining the powerful scalability of the pipeline. But we wanted to add another pillar to it, which is a flexibility. Our platform should be flexible enough in two different ways. One, it should be able to install in any types of user environment. And two, they should be able to adapt to any different types of requirements that user introduces. So these are the evaluation criteria that I set it up. Interoperability between complex requirements, adaptability for infrastructure limitation, and compatibility with open source tools. So the first two criteria is more focused on, can we survive in enterprise environment with, let's say, Azure version of our platform. And third thing is more or less of how we can adapt to future changes of our platform. And let me start by the first criteria, interoperability between complex requirements. So this was actually interesting. This came up because of one interesting ask from our customer. We installed our platform in their AWS environment, actually, but then they had their LDAP structure they wanted to bring in from their infrastructure, and we should support that structure inside of our user base, which we didn't have. So this was a pretty big ask. And then when we talked to another customer, they have another single sign-on request that we had to conform to, and it was a whole mess. And what we wanted to, how we evaluated as our platforms be flexible for this type of environment was pretty simple. We wanted to make our code base, like Python code base, to be adapt to these things, but then we didn't want to change any existing infrastructure to it. And thankfully, that goal was met because we decided to store all these different types of metadata and the requirements on the user's own credentials and authentication strategy inside of the Postgres unstructured database and unstructured fields inside of the database. So we didn't really have to change a lot inside other than the actual Python code base that supports those functionality that they have. And the good thing we had is that since there was no infrastructure changes and like no more layers of a database that we added, we actually didn't lose any performance while we're adding these more supports. The second criteria that we had was adaptability for infrastructure limitation. So the big challenge was that we had to, when we get into enterprise users' environment, they have a specific need. One thing was, one ask that we actually got was this one customer didn't want to use API gateway in their cluster. And the one customer has very specific vendor they're working with all the logging. And we had to change or actually create entire new solution to support this API gateways, data lake engines, and logging structure. And that took us over a month to just conforming with their requirements. But then surprisingly, anything that is hooked up to the Postgres for our complex microservices and data processing pipeline itself, and all the open source tool that is actually user-facing didn't have to change at all. And when they do, they actually ask us to use specific version of the Postgres at most, but that was pretty easy to conform with, and then we didn't have to change any infrastructure other than just changing the version of the Postgres database. So that was a big lift for us. So one lesson that we learned is that if it is hooked up to Postgres, we really don't have to worry about it. The last thing is a compatibility with open source tool. And as a Kubernetes person, my background is more in the cloud computing. When I take a look at open source tools and the possibility of using those, I always take a look at two criteria. One, are they cloud native? And two, if they require internal state management database, and if so, do they support Postgres? Since our platform is built on top of Kubernetes and our primary choice of database is Postgres, we didn't really have to change our criteria from the criteria that I have from my own. And then looking at the community size of the Postgres and Kubernetes, we really didn't have to worry too much about it because, to be fair, all this new technology and all these new open source tools, they do support Postgres and Kubernetes. So at the end, we didn't really have to compatibility with open source tools. So what I found out is just using Postgres itself like boosted our flexibility without us knowing. We didn't have to really change much to meet our initial goal that we lay out. So we were truly ready to move over to Azure adaptation project that we planned without changing too much on the infrastructure itself. The at most thing that we changed was the Python code base to adapt to different types of authentication strategy. But other than that, we didn't have to change too much. Yeah. So now, as a last step, we're going to talk about our Azure compatibility journey. The challenge that we faced was that we expected was we have to find one-to-one mapping of all the AWS services that we're using, including S3. They have to move to blob storage, and DynamoDB has to go to Cosmos. And all this thing, they have a different way of maintaining. Even though they look same, they have a vastly different requirements and some deltas in the functionality. So we need to check those features are there or not individually. And also at the same time, we need to check the performance. If you're losing any performance just because we're switching to other vendor. It turns out what we actually have to change is interesting. So yes, we did have to put a lot of effort on the things that I just mentioned. API gateway, AWS API gateway to Azure's API gateway or API management. They didn't have a WebSocket support, so we had to change a lot of code base to it. And all the logging system was pure pain. But what was surprising for us is that the actual infrastructure that supports AI ML workload that I explained, the 4 pillars of AI ML workload infrastructure, those didn't change almost at all. Like those complex data type management and user interaction, and visualization and data processing between 2 different substrates, those part that was hooked up to Postgres. And since Postgres is not changing when we're migrating from RDS to Azure SQL, we didn't really have to touch actual core part of our platform. At most, what we have to change is how we set up the infrastructure for our computing cluster, and also just Azure SQL instance itself. But other than that, we didn't have to change anything. So there was a pleasant surprise. So in short, yes, everything but AI data and AI workload had to be changed. But then that was within our expectation. So the actual timeline of our migration was pretty impressive, compared knowing that our platform took 4.5 years to implement, but the migration took around 3 months. So we started our technical spec at the end of September of 2023. Development for all those Azure service versus AWS service in Python codebase is done around starting in November. Infrastructure manifest, including Helm and Terraform, that was done around December. And we had our first Azure cluster deployed, first Ikigai platform on top of Azure environment deployed and functioning at the end of January. To summarize it, so Postgres is an excellent choice of database for AI platform implementation, as I mentioned in the starting of this chat, because it enables flexibility, portability, and performance and ease of use. And I highly encourage anybody who's planning to implement AI platform from start to bottom to consider Postgres as your primary choice of database. Thank you. And that's all I had to say. And thank you for joining today.